Alright, draft physics video. Yay. Anyway, I'm going to try to do this in pieces, like, okay, here's certain premises, do you agree or disagree, just to get to the part where something becomes the real issue that's being argued. So in overview, I mean, the first thing to be said, well, I'll do that after, I'll read the comment first and then try to do this in a coherent manner of some kind. But anyway, it sort of responds to Hoffa in a way, also. But there was this guy, Bob Hicks, in the comment section. I'm finally running Linux and it's actually working. Anyway, I'm confused. When did antennas start collecting or transmitting photons? He's actually writing this as a serious comment. Now, Stephen Burrow tried to be a nice guy and explain to him, explain photons and that the whole electromagnetic spectrum is made of these photons because they all travel the speed of light. That's their signature. That's why you call them photons, essentially. It's any little bit that's moving the speed of light, because any other bit that moves the speed of light can't be really anything else, sort of. There's no real way around it. I mean, it has to be something with this, can't be an electron. Electrons don't travel the speed of light. They have a mass issue. Anyway, just very strange that somebody would argue this aggressively. And then so he points out he has some amateur radio license. Says many years ago, while studying for my novice amateur radio license, now a coded tech, I was introduced to the electromagnetic spectrum and its properties. For the sake of clarity and discussion, an agreed upon specific vocabulary was adopted. Radio waves, oscillators, are found at the low frequency end, well, we know that, below infrared visible light, in the approximate center of X-rays, soft, hard, gamma rays. All this stuff is all the same stuff. So there would, so, and he says, again, for the sake of clarity, photons are regulated to the visible portion of the spectrum. I haven't seen that anywhere. I haven't seen that in any physics lecture ever. So I mean, I don't know what your amateur radio guys do, but you obviously aren't you obviously aren't paying any attention to physics, because I haven't seen a single physics lecture where any physicist ever says electrons are what antennas are pushing into the atmosphere, throwing into the atmosphere. Well, anyway, I just found it incredible that he would argue that. But that's how bad things are. People argue stuff that just seems totally insane to other people, and I guess some of the stuff I'm saying seems insane to some people. But at least I'm arguing it. I don't, Bob's going to have a hard time coming up with evidence of the, the electrons that are part of the electromagnetic spectrum. Electrons are what photons hit. So, and there's no other word for them. I mean, calling them waves when they're waves of soldiers, so to speak, they're waves of things. They're not waves. So Hoffaday's doing that in this video a little bit. He's talking about I don't believe in, and he's saying that there's certain kinds of waves, as if I don't believe the phenomena doesn't exist. No, I believe the phenomena exists. It's not a wave, though, because a wave is in a medium. I mean, I've already said that, so that's, I guess, one of these statements that, we have to have agreement on some of this vocabulary. But yeah, I'm not going to, if it's a non-starter for our conversation, I mean, if you're really glued to this idea that antennas are being hit by electrons that are flying through the atmosphere, somehow the charged particles are flying through the atmosphere and they're not going all kinds of other places because they're charged particles. I mean, that's what charged particles do, is they don't fly in straight lines. So, I mean, your chance of getting them anywhere would be really slim, especially getting there on time, because they'd end up going all kinds of places first. So they'd have no consistent speed. So it just doesn't, I'm just saying it's a non-starter for me. I'm not going to switch to your side on that one, okay? I'm not going alien or whatever you want me to, tranny into. I can't do it. So we can just say that we can't really talk about physics because we can't agree on something so fundamental that antennas are not producing or receiving elements of matter, electrons or protons or any big stuff. They're shooting little stuff. They're secreting it like a magnet secretes magnetism. Yeah, those tons are also invisible. Anyway, but that's part of my theory. Alright, so yeah, it's just so hard to, because yeah, you start to say, well, once you start trying to find the rudimentary things to agree on, it just goes forever and ever. So I mean, but one of the things, I guess, number one would be, I think, even if you believe in waves, radio waves, that Hothliday might agree that the wave is an illusion, because we know the wave is made up of elements called photons. That the photons, you might say, are waves. So they're little individual wavelets, but there's no evidence that the entire field of photons is a wave of some kind. The individual photons behave as a wave. Isn't that how the theory is supposed to work? That I could send individual photons through the two slits and it happens, the pattern happens? It's not contingent on a wave of photons, a whole bunch of soldiers. I don't have to have a whole field of them or a whole line of them. I just need one ray of light, one little tiny photon of light, and it will do the wavy thing. So is that agreeable? So we can say that the idea of calling it a radio wave just means there's a whole bunch of waves, not one wave, but the wave front is made of little wavelets. See, your theory is the one that makes things complicated. But let's just agree. Can we agree that the wave is a quantized thing, and that the wave property is held by the individual photons, not by them as a collective? That collectively they don't do anything. They do whatever their waveness is. They do their waviness individually. So if we could agree with that as a premise, then we can understand that when we say there's a bunch of these little quanta of photons, this bunch of photons, you would call them wavitons or whatever, fine. Wave dash photons, wavelet dash photon, can we do that? And once we can agree that that's what's coming towards the antenna, is a front of those, and that represents the signal, and that signal, if it contains a negative component, the negative component's just in the individual wavelet. It's not in the wave front anywhere. There's no, the whole wave doesn't have a wave to it, if you get what I'm saying. If you add up all the little photons, they don't add up to a wave, right? They're individually a wave. They have a wave property of some kind by your theory. I don't know where to put this camera. So anyway, let's just play some of this, and we'll hear him say it, and then I'll say my piece again.
I said I might do it. I thought I'd do it. The radio circuit diagram. This is essentially what we're talking about. I understand Emmanuel doesn't believe in radio waves, just in the same way he really doesn't believe in electromagnetic waves of any kind. That'd be microwave, radar, low frequency, UHF, high frequency, ultra high frequency.
Again, so I don't understand so again, you're just going to keep with this pointless rhetoric. Then fine. You want to deliberately misinterpret everything, fine. I mean, clearly I believe that energy is transmitted using photons at a frequency, and we have a label for these different frequencies. Now clearly I believe in that. And so what's the point of this? I don't believe in your theory, okay? Especially if your theory, like I said, let's figure this out. Do you think that a bunch of those photons constitutes a new entity called a wave? A whole bunch of them equals a wave? Or do you think the individual photons have the wave property? So that would be question 1. Because then we can get to some, maybe we can get somewhere here in the sense that you're denying the quantization. You're saying that Feynman's completely wrong. They aren't corpuscular, okay? That somehow they aren't, the property isn't in the individual photon, this wave property.
Radio waves, TV broadcasts, this is all just bullets being shot in the air. In Mendelssohn's idea.
Well, like I said, I think it's Feynman's idea too. So I'm just saying that, until you get to the interaction part. So Feynman, I'd say, is saying the same thing. He's saying they're individual. It's not a wave. It doesn't. Photons don't spread. They don't do a lot of things that waves do. So it's not right to call them that, especially when they're in a group. They're not tied to each other in some way. There's no evidence that they need each other to perform like a wave. They can perform like a wave as individual single photons. So if we can agree on that, then we can say that yes, we're using different rhetoric, we're using different language and vocabulary, but we kind of agree that the signal being sent is made out of a bunch of photons, maybe 1 billion of them, or 2 billion, or a zillion of them per watt, let's say, of energy that's shot out of an antenna. So say the antenna is shooting out 50,000 watts of energy in the form of these photons, that the photons, each one of the photons as individuals has the wave property, but none of the collections of them at different frequencies has any other new property. Whatever property the quanta have, the individual photons have the property. The collection of them doesn't enhance their property at all. If we can agree on that, then we're basically saying both of us are saying bullets at this point. You're saying the bullet's going to get a little bit magical. I don't let the bullet get magical, you do. But if we can agree that when they're started off from the antenna, okay, they're just individual wave packets, quanta, going in a straight line at the speed of light.
Okay, so it looks like let's find something that I think I can explain my way through easy enough. That fits what I've been talking about. Plenty opening.
Alright, well, he's going to get a diagram and that's going to get more complicated, but that's fine. That's, we're going to have to do that eventually. Let's first understand the basics of what's being argued in terms of the experiment. So I will diagram. So we have 2 emitters, and the signal they're sending is just a radar signal. And what's been done is an audio signal has been placed on top of it, which is essentially turning the radar on and then off and then on and then off at a cycle. So now it has 2 frequencies. It has the frequency of the radar in here plus this other frequency put on top. So these are just 2 frequencies. This is a frequency. Each one of these lines represents a frequency, and this represents an on-off. So this on-off is really slow. On, off, and this on-off is really fast. On-off, 1 billion times faster. Alright? And then we have a receiver that's going to get what that represents. And what I would argue this represents is that these 2 emitters are basically sending out a clump, okay? You could just turn this into clumps, and you could just say it sends out a bunch of clumps, okay, at this rate, and then it sends out, the amount of the clump increases then decreases to 0, then increases to a maximum, then decreases to 0. And so there's no negative portion. There's just the idea that it sends out, say, in this on-off manner. It sends out, let's just say 100 photons, and the next millisecond it sends out 0, and then it sends out 80, and then it sends out 0, and then it sends out 70, and it sends out 0, okay, to do this. Alright, so it's starting off with just 10, then it goes 20, 30, 40, 50, up to 100, then it goes back down again, then it goes back up again, and there's little on-offs in between that, and there's this big on-off. So there's a point where there's always signal for quite a while, until there's a point where there'll be both frequencies will be at null. So there's two on-offs in there, and that's what's being sent. So you could sort of visualize that as, if I was to draw it as waves, okay, then the waves would be, the first one would just be a little 10, okay, and then nothing, and then we'll just make it 50, and then we'll make it 100, and then we'll make it 50, and then we'll make it 10, and then we'll make it 0. And so that's what's being sent out. So 0, then 10, then 50, then 100, then 50, then and then 0. So that's how many photons are leaving. And so that's the signal. So it has no negative component. It just has a bunch of photons, more photons, little offs in between, no photons in between. And all these are exactly the same moment in time. So all of these, this 100 is sent at the exact one moment in time. Pretty close to, by millionths of a second or billionths of a second. They're all sent at that 1/1000th of a second. And then there's nothing. And then there's, for 1/1000th of a second, a whole bunch of them fly out again. Do we agree on that? That's we'll call that premise 2 or whatever. But is that agreeable that that's the signal being sent? That it's all made out of positives and zeros. So it's either a positive or 0. There's no negative component in the actual thing transmitted. No discernible negative component. Can that be stated? There's either a photon or no photon. Can that be understood? And that the absence, the gap in between the photons is essentially the down part of the wave. The up part is the ton being there. The down part is the nothing next to it, so to speak. All right. Yeah. So let's talk about it. So that's the experiment. So the experiment is they put this carrier wave on. Now they didn't have to do that. So the first argument is all you want to do is detect whether radar gets to this receiver when you put it at different locations. So that's all you're trying to do, is to say, okay, if this receiver's at different locations, does it receive signal from these emitters? So the emitters are in phase. That means everything is being sent exactly the same billionth of a second in time. So exactly at the same moment in time, they're sending exactly the same signal out, and it spreads by the inverse square law. So the first thing that Professor Lewin did in his experiment, well, I'm just saying, so let's understand. So they send the signal with this this wave on. Now they could have just sent the plain radar and detected whether they received this frequency. But instead they put this audio signal on, which in my opinion is just a complication that doesn't serve any useful purpose, because they could have just made the receiver make a sound. We can make that when it detects the radar. So that was unnecessary, just totally useless in terms of trying to keep the experiment clean of any complications. So this extra turning it on and off really slow, in my opinion, doesn't help understand the experiment. especially when this carrier, this wave put on top is identical. It doesn't vary, which means that when it does get out of phase, it will be out of phase exactly inverse to its the way it is. There's no, you can't mix the two ingredients. It's always 5 and -5 when they're out of phase. It's exactly the same amount out, so you can't even detect the signals being out of phase, because the audio tone creates a perfectly symmetrical wave. All right, so the first criticism is it's unnecessarily confuses the experiment. So that's one criticism of the experiment. And the next we'll get into the more technical details of this distance. So the argument being made is there's a distance between these things. So let's call this argument 3. Alright, so this is the third argument. Second argument is the nature of the photon. Third argument is, where is this interference happening? So their theory is that these two signals are these two piles of photons coming out, these two fronts of waves, okay, are somehow interfering with each other here in space. So in the space between the emitter and the receiver, they're saying that in that space, okay, these interference lines are created, and that's creating the cancellation, the no signal received at these certain locations because of this interference here in the field. My contention is no, the interference happens here at the detector. The detector can't, essentially I'm arguing that the two signals, once they get out of phase, cancel each other out here, because once they start getting out of phase, they just minus each other. And they're essentially jamming. So one signal ends up jamming the other signal. And that's what's really happening. And it has nothing to do with what happens in the space between them. So I guess the question number 3 would be, can you understand the plausibility that it could be that the receiver can't receive two signals? So when they're out of phase, see, when they're in phase, there's no problem because they're both at the same timing cycle. But the problem is the receiver can't receive the wave at two different timing cycles. It has to say this little frequency here. It has to have a start time and a dead space time and a new, the time when the hit is, where there is a ton, not a ton, is a ton, not a ton. That timing has to be identical for the receiver to receive the signal, because that's how it measures where the gap is supposed to be. It can't know where the gap is supposed to be the reference, if it gets this first thing is not the same. So if the two frequencies are resident frequencies, but they have a different starting time, the receiver's not going to be able to tune them both in. It's going to be thinking this is just the empty spaces are going to be filled with the other signals' start phases, and so then there's going to be no difference, and then there'll be no signal received because it can't see the difference. The reference is destroyed. Or at minimum, it's only going to receive one signal. I don't know. I mean, that's the whole point here, is to try to figure out what the electronics are capable of. He hasn't built a circuit in 20 years. I haven't built a radio in 30 years. So, and even when I did, I didn't have enough. I didn't have the view I have now, in terms of I didn't even have enough technical knowledge to know what exactly the circuit was doing anyway. I just knew you follow the wiring diagram. You know, I was always putting capacitors in without knowing what capacitors are exactly doing. I know more about them now than I did then when I was making such circuits, because I didn't know the theory behind them. I just knew what they practically did, in the sense that you had to have them for a thing to work. I mean, I certainly knew that it was a timing issue. I mean, I know what an oscillator is. You can tell me that oscillators aren't timing, but that's what an oscillator is. It's for timing. Anyway, I won't get into that argument. So I guess what I'm saying, so argument 3 is a recognition that you can't distinguish potentially between interference created in this space and interference created at the receiver, because it can't differentiate, because it's getting two signals that are now out of phase, which seems like two different stations to it. Two stations broadcasting on the same frequency. If you have two stations broadcasting on the same frequency, can a receiver distinguish one from the other if they're out of phase? If they're 90 degrees, I guess it is, 180 degrees out of phase. I don't know, the degree thing I'm probably going to get wrong. But you get it. They're exactly, when one's on, the empty space is where the other one starts. So this is the start of a cycle, is this line, okay? And the point is in the next, this is the cycle. And the point is the other one has exactly the same frequency, it's just the phases are exactly lined up with the dead spaces on the other wave. How would that kind of interference be distinguishable from this atmospheric interference that Professor Lewin is claiming to be the cause, and he is claiming the experiment demonstrates? When I say the demonstration is merely a demonstration of jamming a signal, and that you could have demonstrated it simply by changing the frequency of one of the emitters to the out of phase frequency, and you'll see you'll receive no radar. Even though you know the radar is going out, you know it's hitting the antenna, but somehow the receiver can't interpret it as photons, because there's no absence of photons. The photons have lost their frequency. So you can see if this lines get filled in, this is now the wrong frequency. This is now double the frequency that it was before. So you'd have to detect it by detecting double the frequency. So that would be maybe a good test. Does it work if you do this and you find the place where the signal can't be picked up, no signal, and then if you leave this exactly at that location and tune it to twice the frequency, will you find a signal there? I mean, there's a ton of, this is a really good, I mean, I should buy one of these radar setups, because this is a really good way of testing this interference theory, because at least you can change. I mean, unlike a double slit, you can't vary the frequency of the stuff coming out. You can't do anything. Here you can adjust them and see if you can find some adjustment that reveals where this interference really happens, at the receiver or in the atmosphere. All right. Sorry, I mean, it's going to get long because it's complicated. So anyway, yeah. So the Steve Burrow guy did leave a long comment. I'm not going to read the whole thing. He types a lot. I mean, I should get him to try to write my book, because he obviously can write and write and write and write. So I hate writing. I just have learned to. I just hate it. Anyway, so he's, but I disagree. I had to think a while before realizing the main flaws in the argument against interference in the radar signal versus the audio signal it carried. Again, I wasn't arguing that this signal per se is interfering, that the audio signal was interfering with the audio signal. I was always arguing that that was happening because of the carrier interfering with the carrier signal, in the sense that the audio signal is exactly perfect. So like I said, so let's say this is how the audio signal looks. Okay, the point is the signal being interfering with it would have exactly the same amplitudes and exactly the same location, right in those middle locations. So the destructive interference, so to speak, would be perfect to the audio. It would just kill the audio entirely, because there wouldn't be anything left over. See, if the audio signals were different, then you'd have little pieces that would stick out, and you'd be able to pick up those little pieces that would still stick out at the right frequency. That was my point.
Okay. View image. Right. Now, here's what we're talking about, is the tuning circuit. This is the arrow through a variable capacitor, and you have an inductor, and you have an antenna. The tuning here, when you hit the resonant frequency for the carrier signal and everything on the carrier signal is, in a sense, amplified.
Well, no, it's not amplified. It's segregated. So it's still, it has to be amplified after it's captured. So first it's got to be captured and then it's amplified. So you don't have that in the right order, in my opinion. There's no amplifier here. This transistor is turning on and off. Here's the amplifier here, and then it goes into the integrated circuit. Of some kind anyway. It looks like some kind of more complex circuit, which must have a diode in it somewhere, because they have to cut the bottom of the wave off. But anyway, so let's talk about what happens in the first part of the antenna. The antenna is, so this will be number 4. Let's see if we agree on this. So the antenna is just sitting there in the atmosphere, and it's getting hit by a zillion tons a second. I mean, they're hitting from all over the universe. Everything's hitting this thing, blah, 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 blah. It's just getting the shit kicked out of it. And those hits turn into an electrical signal, an on-off, right? So different kinds of frequencies are coming down this wire in the sense of electron frequencies, voltages. All right, and the point is you want to try to trap a specific voltage. So let's see if we can agree on a kind of a metaphor for it. So what's going to happen is there's going to be little balls coming at something at different frequencies. Okay, they're going to be all kinds of varying frequencies, and the point is you want to catch a frequency of a certain length. Okay, so to say this is the radar frequency, you want to catch it in this box. All right. So let's just make this a box and say we want to catch it inside the box. Well, what the box is going to do, so as this electrical signal is sent here, it's going to try to capture it. And so by capturing it, what it's going to do, essentially, right, is say, let's just put it puts a little block, a little net up or something, whatever you want to call it. And it says, did anything hit me there? Or let's the thing hit the net, let's say, or the tube. It just puts the tube up. And let's just say it's a tube. Okay, so it's a tube that just sends it down this new wire. And so it just it opens this tube. Okay, this tube, let's say, is just rotating. So there's a hole that the little thing can go through at this speed. Okay, and so that's the resonance. So once we have a resonant speed, that's the speed the hole will open. And so it just says, okay, feed me these electrical signals, okay, these little pulses from electrons, and if it goes through the hole, that will represent something being the first one. going through the hole. And so obviously the hole would go around and it would be the same cycle as this. So the hole would show up, and if another ton comes through, I mean another electrical signal, then it would know that it's catching a frequency. There's some signal there. So it goes around again. And if another one goes through it, just that millisecond, well then it knows it's caught it. It's caught a frequency. So it's taking the electrical impulses and converting them. These still might be tons actually. I mean it's an electrical voltage is force more than is electron. So let's understand, it's probably not electrons that are going through this thing. It's the force is going through them as transmitted by the electrons. So they're still an essentially ton, and they're not quite electricity yet. They're electricity, but it's the stuff in between the electrons. I mean, that's the part that gets it. So we don't have to agree on that. Let's just agree on there's a energy. Okay, so it's taking the little pieces of stimulus. Let's just call it the stimulants. I don't know. We have to find a word for electron or the force between the electron. You know. Anyway, so that's the idea of a resonant frequency. Is you're really just trying to trap something in a certain length or distance, and only something that's coming at that rate can get through this trap, if you get my drift. Now the trick to this tuner is that, again, we're back to this phase argument. So if this thing's not at the same phase as this signal's coming through, then it's not going to receive this signal. So if the photons are coming at this rate, you know, they're exactly at the right frequency, but their starting point is different. The trick is, how does this resonance box know how to catch any phase of this frequency? How does it know when to start rotating to get that right? And I think that has something to do with it seeks that. The circuit by its nature finds where the most photons are at that resonance somehow. But then you're going to have to understand exactly what the inductor does and exactly what the capacitor does. You know, the two components, in terms of how they're pushing and pulling on each other to create this trap. But somehow the dominant amount, the dominant phase, is the phase that'll be let through. So whatever one has the most force at that frequency is the one that gets through, I think. Because obviously the only thing you're tuning is frequency. So what you don't, you know, the tuner allows you to get to this, to get only things coming at this rate. This is a timing rate, distance between these things. That's all time. And all the frequency, all the tuner allows you to do is to change how far away these things are. See, I can move them, I can make them tune in a bigger or a longer and a longer frequency. So the tuner allows me to tune in what frequency, but it doesn't let me tune in at what phase. So catching getting the phase right is the part I don't have the answer for at this particular moment. I don't know how the circuit does that exactly. And I assume it just picks whatever the strongest signal is of all the things that are at resonant. So all the things that are at the right frequency, it only grabs the one that has the strongest signal somehow. Alright, so I thought there was a number 4 in here. So maybe number 4 would just be, can we agree on that basic nature, that's what the capturing circuit is doing, is it's just basically saying only one signal's getting through. Basically. Only one at one phase. And that's a question we still have open. Alright, so number 5, I just thought of one of the first things, the other thing that still hasn't been answered about the Professor Lewin experiment. So without going into the details of the fact that, okay, what basically the experiment says is when you get to these different locations, there's no audio signal, and the assumption is because there's no audio signal, there's no radar signal, and it's the radar that got interfered with. And as I'm arguing, no, both of them got interfered with. But anyway, it's, they didn't interfere out here is the argument. All right. Well, the other part of what he did was he blocks one of these. So when the receiver is in the middle, so it's halfway between these two. All right, and the signal's heard. He covers one of these signals, and the sound reduces by 1/4. All right. Now, that would work if it was a two-slit experiment, in the sense that, yes, a lot of the signal goes straight through to the middle, so, even then it still doesn't make sense. So we still haven't explained why that happens. What about being in the center and blocking one of the emitters when they're in phase? Why does the sound go down by 1/4? I mean, we both have an explanation for why when there's no sound and you cover one of them, the sound comes back because you're no longer jamming the signal. But why that 1/4 reduction in sound when you cover one of the emitters? So that's number 5 is a question, not asking for agreement on a principle. All right. Continuing, I suppose.
Right. So that means this tuning circuit and the theory behind this, how this works, all worked out in classical mechanics and agreeable with quantum mechanics, says that this thing is looking at waves coming in. Yeah? And the waves come down.
All right, so you want to keep saying they're waves. All right, so there'll be a point where we just say, okay, we just can't agree on what's really happening. There's I'm not going to, I mean, it's silly to me to say waves are coming down, because we don't call it waves of electricity. We don't call it that stuff. I mean, most people don't. There's no idea of waves. There's an idea of actual electrons moving, and they're not waving somewhere. They're moving in a direction, and they go this way, and they go that way. They go this way, and they go that way. I mean, when you're talking about an electric circuit, it's kind of lost the wave thing. Okay, I mean, we can understand that the wave is just a synthetic representation of the fact that one part of the signal goes, like when they draw the sine wave for AC current, you know that there's no wave there. There's current going this way, and then current going that way, and then current going this way, and current going that way. It's not really a wave. So, I mean, it's just not helpful if we can't, come to some agreeable terms that there's a quantity of energy coming out of the antenna, and that there isn't any such thing as a negative energy. There's just some sort of positive energy.
As waving electrical voltages from the earth, pure and direct.
So so I would argue that all there can be is the on, and then you can say that the off is a reversal. On, then off is a reversal. So if you want to say the off part is where it goes back to neutral or something, fine, we could agree on that. But there's no true negative.
So you've got a wave in the earth, you've got a wave in the voltages, but you've got many other voltages there, potentially, from many radio stations, from TV stations, from...
Yeah, so maybe we should just use the word a voltage. Once it hits the antenna, the quanta are converted into a voltage. And then we'll just leave the word wave out of it.
Microwave, from your Wi-Fi, all hitting the same antenna. Right? So this is tuned, and it will just instantly boost beyond comparison. All those tiny, minute micro voltages. That's micro, point. Yeah, milli.
Okay, so his argument is that the resonator, okay, is going to boost this signal, where I would argue that, well, the boost is in the form of segregation. This will be obviously seem very much louder when you take all the noise out. So compared to the noise to signal ratio will be hugely improved here, which is just, you could argue, is like amplification. Whether it's truly amplified or not is an issue for argument. And that goes for all resident circuits or instruments even. It's not like it's manufacturing more energy. It's just allowing the energy to turn into sound. It's not that the energy wasn't already doing something else. It's just converting it in like a resonator converts the energy that already exists into a sound. So it's not making more energy, in my opinion. But it doesn't matter to me. Fine, if you want to say it amplifies the signal to make it unique, so it's much louder than the noise, or if you want to say it eliminates the noise, therefore making the signal louder, I don't think those semantics should get in our way.
Millivoltages or microvoltages, unsure, but basically a couple of zeros before you hit the point.
Yeah, well, it's milliwatts, so they always count it in watts. So yes, it's a tiny milliwatts. So megawatts were sent from the antenna, 50,000 megawatts. And all you're going to receive is 10 milliwatts of the radio signal. So if 1 billion were sent, you're going to receive 15, something like that. That kind of ratio.
The decimal place of the voltages. So the micro voltages on all those other channels, and this circuitry will boost the bigger circuits perhaps to millivolts, which is just 2 zeros. Now the macros being like 5 zeros before.
Well, again, what voltage it's at, I don't think is the question. I think it's what amperage it's at. So it's more of a wattage question than a voltage question at this point. But it doesn't. Again, I don't think that matters. I think the voltage is probably 2 or 3 volts. It's just at a tiny amperage.
The significant figures, and it does it not in a counting way. That's how it does. Now, this is an amplifier step.
So he says not in a counting way. Well, my argument is that that's fundamental to the system. Of course, it's in a counting way. It counted at 1 zillion second. It just says how much energy hit the antenna. It's at this capture point. So the little hole goes open, and how much stuff got through that hole. I mean, each one of these little things represents an amount of stuff. So the voltage is going to be the pressure, which means the higher the voltage, the more stuff that's going to go through the hole, because it's got more speed. So as the hole goes through, the faster the stuff's coming through, the higher the voltage pressure represents more stuff. So again, it is so 6 would be, you're still going to contend that a voltage isn't a representation of an amount of something that hit something, that went through the system. That the voltage is going to tell you how many, it's a representation of how many photons hit the antenna at that exact moment in time. You disagree with that?
Also, you've got it's called something I forget that this is a standard configuration of transistors usually, and it's called something when you stack them like that to get you extra amplification. Anyhow, so there's even more amplification.
Yeah, well, this one's the one always coming in perpendicular is the switcher, and the power it's switching is this one. So this is just switching the circuit. So, and then they sometimes feed them funny, but anyway, so and then it's feeding the same switching circuit is getting fed into this transistor, which is feeding the power circuit, which is fed by this capacitor that pulls the juice off the main circuit. So the main circuit's going to pull the juice here with a capacitor into this transistor. So this is the one, the power transistor. This is the transistor that's taking the what comes out of here, an amp. That's a preamp and then the amp. You could call them.
Amplification fed through a capacitor, which is removing a DC component. Okay, it's blocking the DC because you supplied a voltage here. You actually are riding on top of a net DC voltage, and you're amplifying, kind of putting a noise on top of a basic DC level, which is amplified through the transistors, and then finally you kind of cut out that voltage and just...
Yeah, no, I think this is a pulling capacitor. This is just pulling to feed this, to pull the signal from here into here. It's giving it a place to go. But anyway, it doesn't really matter, I don't think. I don't see, like I said, this circuit isn't revealing. I mean, this isn't a really great circuit because most of the circuitry is in this triangle. So we're not seeing all the other buffers and what do they call it? Something sandwich. They have some word for the part that envelope, some kind of envelope circuit.
Below the AC component with this common reference.
Well, the other, and yeah, see, there's a circuit that cuts the DC off, actually, that cuts off all the negative current. I mean, all the negative voltage. And that's in my opinion, that's the circuit that's trying to find this dead space in between. So when it's cutting off the second half of the wave, let's say that's number 7. Can we agree that in principle that the dead space in between these ons is essentially going to get represented as this portion of the wave. So the wave, this portion represents this portion of the wave, the on part represents this portion of the wave. And what's going to happen in the circuit is this is removed. And I would argue it's not really removed, it's subtracted from this. So this is subtracted from this, and what's left over is your signal. But anyway, you don't have to agree with that part, just agree with the, as a representation, the bottom portion of the wave is essentially this portion of the frequency.
Ground to enter an operational amplifier, and this amplifier, op amp, then is generating to headphones or loudspeaker, and you hear the sound. Right?
Yeah, well, it's really short a couple of components there, quite obviously, in my opinion, because they do need to. There's a circuit that has to clean this up. So, like I said, I'll have to go find a better diagram. But maybe he does. So we'll play some more of this, and then we'll just wait for a part 2 or something.
Where's the filtering occurring of...
I mean, see, look at his title again. He just keeps doing this provocative. He just can't let it go. Every single video he has to title like he's a fucking 2-year-old. Explicit rubbish of daft AM radio. Is he really demonstrating any of that in this? Is he demonstrating this huge superiority where he has some right to call somebody daft or an imbecile or completely insane or so stupid? Does he have anything in here demonstrating any of that? I mean, it's this stupid idiot. It's like the idiots who have a screen name say, I have a 12-inch dick. I mean, you're just an idiot to make these preposterous claims that you're doing something in these videos to demonstrate something. What are you demonstrating here? That's some sort of, I've proven wave theory now. See, this proves wave theory. No, it doesn't. Not even close. Alright, it's almost out of time.
So here we must have the total AM signal. Perhaps this works somewhere to filter out that, and the audio signal is existing, going the audio only. So you know.
I mean, this is drawn as a resistor, but it could be it can't be a diode. They wouldn't draw it that way. There's got to be a diode in here somewhere, and there isn't.
I'm not an expert on this, but you could read about the details about it.
Oh yeah, okay. You could read about the details written by people who don't really, have also not necessarily a correct understanding of what's even traveling through a wire, or what a voltage is, or any of that stuff. So, what good would that do? I mean, the only way to do this is, I think, is I'm going to have to test it with some other mechanism where I can adjust these frequencies and do this. But I mean, or we could ask MIT to do it. Plead with them, please, put two different frequencies. Put a subtly different carrier on your radar, and then see what happens. And subtly change the, in some way to try to make a distinction between jamming a signal and true interference.
Yeah, at some point. But transistors are used as switches and amplifying devices.
Yes, oscillators use them also.
Okie dokie. Now this corresponds in no way to how a Mendel would like it to work.
Yeah, haha, your video's out of phase. Haha. It's ironic. Your video's out of phase. So again, did he do any of that? Did he show how this is not consistent with how I say it works, or do any of that? No, he didn't do any of that.
That's receiving. And you see, it's a pretty much, similar schema, similar architecture for whatever,
Okay, so look, let's just go, just in a little tiny bit of time left. So go back to question number 5, which is, why don't you explain the 1/4? Okay, because Professor Lewin didn't, and it was disappointing. They said, well, I'll test you on the final on that if you really understand interference. Why is it 1/4? Why, if I block one of these transmitters, does the signal go down by 1/4? Why does that happen? Because, yeah, there's no reason. You can't make sense out of it. I can't make sense out of it as jamming. These two signals can't possibly be jamming each other, because they're both in phase and they're both going to the same central location. So there'll be a tiny bit out of phase, both of them, but they'll be the same exact amount out of phase. So there's no way they can't be perceived as a good on-off signal. They won't be jamming each other. They won't be sticking stuff in between the frequencies at all. So the frequencies will be nice and clear, and they'll both be received as essentially the same exact transmitter. It'll look like, to the antenna is going to say, I'm getting hit by exactly one transmitter. It's not going to know the difference between the two. It's going to feel like one transmitter shooting twice as much stuff at me. And that's if you detected the actual radar instead of the audio, peeling the audio off, because the audio won't get doubled. But quite realistically, but the carrier signal will definitely be doubled. So why don't you explain that one, and then we can go somewhere from there, because I don't have an explanation for what he meant by that 1/4 thing. And he showed it happening. I'm just saying. So it does. We say, okay, it happened. Why? All right. Till next time. And such. But no doubt a necessary part too. I'll play the rest of this video. I guess I won't do this for the rest of the video. But we'll see where it goes. I think the 7 things to disagree about are already enough. And then we can find out where there's, there's just no point in having the conversation because you think we can't agree on what's moving and what's creating voltages. Photons are creating voltages, and the voltage is commensurate to the amount of photons. It's measuring the photons. It's weighing them. It is.